So we call this the standard normal distribution curve. You might want to bookmark this because this is going to be an important page to come back to. For population data with a mean of mu and a standard deviation of sigma, the normal curve is denoted by, normal curve is mu bracket sigma squared. There is a different probability distribution for every value of mu and sigma. In order to compare normal curves and to solve probability problems involving normal distribution, we convert the normal distribution curve given in a problem into the standard. Here's really important. When we're using the standard curve, a standard curve always has a mean value of 0. So this middle value is just going to become, as we see right here, 0. We start at a center point of 0, and every standard deviation is going to be 1. So I went up 1, up 2, up 3, down 1, down 2, down 3. Every single time it's just up 1 or down 1. And this is just for the standard deviation curve. The equation of the normal standard deviation curve is f of x is equal to 1 divided by the square root of 2 pi times e to the power of negative 1 over 2 x squared. You don't need to know that. Verify the bell shape of the curve using a calculator window of this. Well, you can plug it in to your calculator. There is an E button, and you can see that this is going to be the same. The terminology and the equation of the standard curve are not required for this course. That would be if you're going into a more advanced statistics course. But this part is important. The diagram shows the approximate area under the standard normal distribution curve subdivided into regions with a width equal to 1 standard deviation. So, like we said, when we took a look at our curve, it was pretty close with all the data in here. If we take a look at the normal curve, it's going to be just a little bit off, but still pretty close to the range. So the mean of this data is going to be 0. The standard deviation of the data is 1. That is always true for this curve. If I want to say how much of the data is above the mean, well, if I'm looking for this entire area above here, if this is a perfect bell curve and the mean splits right in the middle, then that area is always going to be 50% is going to be above, which means that 50% would also be below. How much data is within 1 standard deviation of the mean? Well, if I account for 1 standard deviation above and 1 standard deviation below, I'm just going to add those together to get how much area combines for 1 above or 1 below. And I'm going to say that it's going to be 68.26%. How much is within 2 standard deviations? Well, I'm going to go 2 standard deviations below and 2 standard deviations above, and then just add up all those percentages. And in this range, I find that I have 95.44% of the data. If I expand that out into 3 standard deviations, all the way through there, then I'm going to have 99.74% of the data. How much of the data is between 1 and 2 standard deviations above the mean? Well, just 1 and 2 standard deviations above is going to be this, which is going to be 13.59%. And if I do the same below, it's going to be identical, 13.59%. So, just a quick review. The basic properties of the curve. The total area under this curve is going to equal 100% or 1, if I represent 100% as a number. The normal curve extends infinitely to the left and to the right, which means that we'll never actually hit an endpoint because we could always potentially add more data. But if we went on to infinity, then it would. The normal curve is symmetrical about the mean, which means that half is going to fit on the left-hand side and half is going to fit on the right-hand side. All the data is represented by the area underneath the curve, which is going to be a total area of 1. And the mean, the median, and the mode of a normal distribution curve are all going to be the same. They're all going to be 0. So anytime that I turn it into a standard normal deviation curve, the mean, median, and mode all become 0 instantly. Okay. Let's put this into practice. A nurse records the number of hours an infant sleeps during the day. He then records the data on a normal distribution curve shown below. The values shown on the horizontal axis differ by 1 standard deviation. So, if I look at this, and I'm actually going to fill in these lines just a little bit thicker so it's easier to see. If it's asking for what is the mean of the data, the mean is going to be in the dead center. It's going to be mu is equal to 12 hours. What is a standard deviation? So to go from the first line to the second line, how much did I go up by? I went up by 2 hours. If that is true, what are the values for A, B, C, and D? Well, I'm going to just keep moving backwards. This was 12, 10, which means that this would become 8 and 6, or 12, 14, 16, and 18. What percentage of days to the nearest hundredth does the infant sleep between 12 and 14 hours? Well, because this is based on a standard deviation curve, if I needed to, I could scroll back and say between 1 and 2, that's going to be 34.13%. What about between 8 and 16 hours? Well, that's going to be between 2 below, going all the way up to 2 above. And we already answered that. Within 2 standard deviations, that is going to give me 95.44% of the data. What about less than 6 hours? Well, that's going to be in that extreme range here. And we said that that was 0.13% of the data is going to fit in there. Why is it not possible at this time to determine the percentage of days the infant sleeps for less than 13 hours? Well, 13 hours would be in here. If I wanted for less than that, then that would be this whole range here. But the problem is I don't know for half of this point. So the reason is we do not know the area under the curve for partial deviations. Only for one standard deviation. So far we've only taken a look at the percentages for one whole standard deviation. In order to do partial deviations, we need to take a look at z-scores, and there's an entire table at the back of your book which you're going to want to make reference to all throughout the next lesson. It is not possible, given the curve in class example 1, to determine the percentage of days the infant sleeps for less than 13 hours because the model of the curve is limited to integer values for standard deviations. The concept of z-scores can be used to determine this percentage, and a z-score for a particular set of data is the number of standard deviations above or below the mean. So that big fancy z-score table at the very back of your book breaks down into hundreds of standard deviations so that we can solve that. If I am calculating a z-score, consider class example 1 with a mean value of 12 and a standard deviation of 2. The data value 18 is going to be 3 standard deviations above the mean score, which means that it has a z-score of 3. The data value for 8 is going to be 2 standard deviations below, so the z-score is going to be -2. The negative indicates that it's going to be below the mean. 12 is 0 standard deviations away, so it's got a z-score of 0. It's easy enough. And 13 is half a standard deviation above the mean, which means it has a z-score of positive 0.5. If I'm putting that data into the normal curve, then I could say, well, in terms of mu, that if this is mu, this is mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, or mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. This would have a z-score of 0, 1, 2, 3, or -1, -2, -3. And if I included that point of 13, then 13 would be the same as mu plus 0.5 sigmas, or a z-score of 0.5. How can the z-score for a data value of 13 be determined? Calculate the z-score for the data value of 13 and list both the data value and the z-score on the normal curve, which we've already done. Z-score of 13 is going to be equal to 0.5. It is halfway between those 2 points.